I want to look at a problem that we've seen many times before. This is a bullet being fired into a block and becoming embedded in the block. We've seen this problem before, and we've even analyzed it to figure out the thermal energy generated. But now I want to take it a step further, and we're going to assume all that thermal energy goes into heating up the bullet, and I want to find out how much the bullet's temperature changes. So to begin with, we know that this is just conservation of momentum. And so initially, the initial momentum has to equal the final momentum, and initially we have the bullet. And afterwards, we've got the bullet plus the block. And so the values for the masses and the initial speed, that's all given up above here. So the mass of the bullet is 10 grams, so that's 10. The initial speed is 200. Okay. And then I'm taking that 10 grams and add it to the 990 grams of the block. Solving for V final. So this is going to be 10 times 200 is, 2,000. And I'm going to divide it by 10 plus 990, which is 1,000. So divided by 1,000, that's going to equal V final. And that's going to end up being 2 meters per second. So now we can move on to energy analysis. We can use conservation of energy. Delta PE plus delta KE plus delta TE equals 0. And again, you've done this all before. In this situation, there's no change in potential energy. Now, other situations that might not be the case. There might be a change in potential energy. You have to look at each situation. But in this situation, no, there's no change in the potential energy, so this is 0. So we know that we do have a change in kinetic energy, and we know some thermal energy is generated. So I can say delta TE is going to equal the negative change in kinetic energy. Okay, well, the change in thermal energy, that's going to be just the temp due to the let me rephrase that. The thermal energy generated is going into heating up the bullet. So I already know how to calculate that. That's going to be just the mass of the bullet. The bullet is, I stated over here, the bullet is copper. So I need the specific heat of copper. And of course, the temperature change for the bullet. And that's going to equal the negative change. So this is the final kinetic energy minus the initial kinetic energy, because change is always final minus initial. The mass of the bullet. Now, before I didn't change the mass to kilograms because way over here I left this in grams because I knew I was going to take these grams and I was going to divide it by these, so it didn't matter. That was going to cancel out. The only unit that mattered was this needed to be in meters per second, which it is. But here, the mass of my bullet, I'm going to have the specific heat of copper, which I know in terms of kilograms. So I am going to convert the mass of the bullet to kilograms here. That's just 0.01 kilograms times 377 times the change in temperature. And this minus sign can be distributed. So this is the initial kinetic energy minus the final kinetic energy. Okay. And 0.01 times 377 is 3.77 times the change in temperature. Okay, so this becomes 1/2. So initially it's just the mass of the bullet, its initial speed squared, minus 1/2. So I've got the mass of the bullet plus the mass of the block plus my V final squared. Okay, so 3.77 delta T, 1/2. And again, although I didn't do this before, I do need to change the mass to kilograms. And it all comes back to my unit analysis again. I'm using MKS units, and this time specifically this 377, besides being in terms of kilograms, it's in terms of joules, and joules is defined in terms of kilograms. So I need to make sure that my kinetic energies are coming out in joules. So that means my mass has to be in kilograms. So this is 1/2 times 0.01. The initial speed is 200. So 200 squared minus 1/2. Now I already know that the mass of the bullet plus the mass of the block, we already figured out that's 1,000 grams, which is 1 kilogram, so that's just 1. And V final is 2, so 2 squared. Okay, so 3.77 delta T equals, and so here we're just I'm gonna crunch these numbers real quick. And this works out to be 198. When you multiply these together, then subtract 198, and that would actually be joules. I've done it, so these are energy units of joules. And then delta T is, of course, going to be 198 divided by 3.77, and that's going to be 52.52 degrees Celsius. Now, I chose to write degrees Celsius, but let me just add, I could have also said 52.52 Kelvin, because we're talking about temperature change. Right? When you're talking about temperature change, a temperature change of 1 degree Celsius is the same as a temperature change of 1 Kelvin. So as long as you're talking about temperature change, it doesn't matter if you put Celsius or Kelvin. It's the same. It only matters if you're talking about the actual temperature. I'm not saying the actual temperature of the bullet is 52.52 degrees Celsius, nor am I saying it's 52.52 Kelvin. I'm saying the temperature changed by this much. Thus, we can use degrees Celsius or Kelvin. But this is how you go about solving such a problem using conservation of energy, where we could potentially have potential energy. We didn't here, but we had kinetic energy, and we can go through and figure out the thermal energy that was generated. Okay? In this case, it turns out 198 joules of thermal energy was generated, and based on that, I can figure out the temperature change, or if I was solving for specific heat or whatever I'm asked to solve for. But this is the idea. This is how we use conservation of energy in conjunction with calorimetry.